This is our second lecture on approximation methods in quantum mechanics. And in this, we are going to continue our discussion of the variational method. In the last lecture, we introduced the variational method. We explained how you would use it to determine bounds on the energy eigenvalues. And we also went on to give a few examples. We took some very simple examples like the harmonic oscillator and some non-trivial ones like a quartic oscillator. And in the end, we also described how you could find out a lower bound of the energy eigenvalues. Remember, the variational method gives you an upper bound. And so if you could find a tight enough lower bound, that would mean that our energy eigenvalues are pinpointed to a very narrow range. The technique that we talked about in the last class, just using the variance of the Hamiltonian, turns out to be a bit too generous as far as error estimates are concerned. The lower bound that you get from that calculation is a lower bound, but it typically is rather too low to provide a rather nice tight bound on the energy eigenvalue. In this lecture, we are going to learn about a better way of putting up a lower bound on the energy eigenvalues so that we get a much more precise idea about what the energy eigenvalue actually is. We will also see a few more applications of the variational method, including its use to derive a very important theorem. But before we go there, let me point out one thing. Many of you may have already wondered about the fact that the variational estimate seems to be doing much better in many applications than it should be doing. You may be using a wave function or a family of wave functions which has some of the broad features which a ground state wave function of a system must have, but may be quite different from the actual ground state wave function. And yet the energy estimates do turn out to be quite close to the actual value. So let us answer the question now. Why does the variational estimate perform better than it is supposed to? To answer this, let us take a look at the situation where the final ket that you have, the ket which extremizes the expectation value of the Hamiltonian, the ket psi, differs from the actual ground state wave function, phi 0, by this amount delta psi. Now, if your choice of the trials family of wave functions has been judicious, then you expect that in the end of the day, delta psi will be somehow small. Anyway, if you were to calculate psi h psi, the expectation value, you will get bra phi 0 plus bra delta psi, sandwiching h, and phi 0 plus delta psi on the other side. So this breaks up into four pieces. As you can easily see, the first piece does not have any delta psi in it. Then you have two terms which have a single factor of delta psi and a final term which has two factors of delta psi. Using the fact that the Hamiltonian acting on phi 0 is E0 phi 0, phi 0 being an eigenket, it's easy to see that this term is E0, and it's also easy to see that you will get a factor of E0 coming out from both of the terms which are linear in delta psi, so you are left with E0 times this overlap phi 0 delta psi plus delta psi phi 0. Of course, this is really twice the real part of phi 0 delta psi. In addition to that, you have an additional term which is quadratic in delta psi and which is typically rather small. So the variation between the expectation value of the energy and the ground state energy is dominated by this term, which is linear in delta psi. At least it should have been dominated by this term. What happens is that this term actually is 0. To see that, let me point out that the ket psi is normalized, right? So bra psi ket psi is 1. Replacing the value of psi by phi 0 plus delta psi, once again, what we get is that this term has to be 1. This splits into 4 pieces as before. One piece which is independent of delta psi, 2 pieces which are linear in delta psi, and one more piece which is quadratic. Now notice that this 5050 is actually 1. So we can cancel these two sides out. And that tells you that 50 delta psi plus delta psi 50, which is the factor which was telling you how much your energy changed or expression value of energy differed from E0, is actually only order delta psi square. In fact, it's 0 to the first order in delta psi. And what that means is the deviation of the expression value of the Hamiltonian from E0 is not first order in delta psi. The first order term cancels out. What you are left with is a second order correction. Note that when the wave function differs from the ground state wave function by a first order term, the energy differs by a second order term, which is why as long as you have got reasonably close to the ground state wave function, your energy is going to be a much better estimate to E0 than you would otherwise expect. So now that we have understood why the variational method ends up performing much better than you would otherwise expect it to, let us turn to the question, just how close is the variational estimate to the ground state energy of a system? Let me remind you that we had already figured out one way of doing this, which was using the variance, as I said a while ago. And what we concluded was that if you calculate the variance in a state, then there has to be at least one energy level somewhere between the expectation value of energy minus square root of the variance and expectation value of the energy plus square root of the variance. And by using that for our quartic oscillator, what we found out is that there is an energy eigenvalue between 0.246 and 0.835. The variational estimate actually was the value 0.541. And although we could not be sure that the ground state energy between 0.246 and 0.541, we were reasonably certain that that is exactly what the situation is like. So we do have a lower bound here, but the lower bound really is not very tight. Right now, from this value, from this result, we cannot be sure how much to trust our estimate of 0.541. After all, the lower bound we have calculated is less than half of this value. So we have a sort of 50% error interval within which our energy could lie. So can we do better than this? The answer is we can. We will now talk about a method due to George Temple, which allows us to estimate a rather tight lower bound on the ground state energy. In fact, as Cato had shown, this actually is one of the tightest and the best estimates that you can really have without actually exactly solving for the energy eigenvalue. Temple's method hinges on this particular inequality that you have on your screen right now. What we are doing is taking the kets H minus E1 psi and H minus E0 psi, where E0 and E1 are the ground state and the first excited state eigenvalues, the actual eigenvalues for the system, and taking the overlap. And it's very easy to see that this overlap is simply given by this particular infinite sum here, where the sum actually is over all n, but frankly you could just as well use n to be from 2 to infinity, for the simple reason that the terms for n equals 0 and n equals 1 actually vanish because of these two factors of En minus E0 and En minus E1. And since the energies form an increasing sequence, En minus E0 is positive for all n between 2 to infinity, so is En minus E1. Cn mod square of course is positive, so for this sum, every summand is positive, and the lowest they can be is 0, and this shows that this particular overlap is greater than or equal to 0. It will be equal to 0, of course, only in the situation where the state psi can be expanded only in terms of phi 0 and phi 1, the lowest two energy eigenfunctions. Now, if you expand this out, again you are going to get 4 terms, and it's pretty easy to see that these 4 terms will be d psi, which remember is actually psi h square psi, minus E0 plus E1 times curly E psi, which of course is psi H psi, plus E0 E1. And just by supplying a minus E psi square and a plus E psi square here, you can easily write this in a useful form. The first two terms gives you the variance, right? This is the expectation value of H square minus the expectation value of H squared. So this is the variation in the Hamiltonian, what we have been calling sigma. So what we end up with is this expression. Sigma plus these three terms together factorize neatly into E psi minus E0 times E psi minus E1, and this is greater than equal to 0. Now if my system doesn't have an energy level E1, the first excited level, very close to E0, and if my variational method family of trial wave functions is at all judiciously chosen, then we would expect curly E psi to be more than E0 of course, but also to be less than E1. To go beyond E1, you would really need to be pretty bad in your choice of trial wave functions. So let us assume that curly E psi lies between E0 and E1. Then it's pretty easy to see that this inequality can simply be rewritten in this form, that E0 must be greater than or equal to curly E psi minus sigma by E1 minus E psi. If anybody is wondering about the minus sign and this E1 minus curly E psi rather than E psi minus curly E1, the factor here, let me just remind you that you have to be careful when you are manipulating an inequality by multiplying or dividing by something, because you have to make sure that what you are multiplying or dividing by is positive. If not, you would have to change the sign of the inequality. And note that our assumption really is that curly E psi, which, okay, this part is no assumption, it has to be greater than or equal to E0. We are assuming that our choice of trial wave function is good enough so that curly E psi is actually less than E1. So what we end up with is this result. So we get a lower bound on E0. Of course, it may seem a bit difficult to use because the lower bound actually depends on the value of E1. And as we will see, that will produce some technical hurdles in actually using this. But we will be able to figure out pretty nice tight lower bounds using this, as our next calculation will show. We now apply Temple's method to our old friend, the quartic oscillator. And let me just remind you that we actually solved for the variational estimate for the ground state energy in the last lecture using a family of normalized Gaussian wave functions. The calculation ended up being rather straightforward. The curly E of alpha, the expectation value of the energy, came out to be of this form, which was minimized for alpha given by alpha 0, which is cube root of 3. And when you plug this in, you end up with this value for the variational estimate of the ground state energy. That's 3/8 of cube root of 3, roughly 0.541. So this is of course something which we have already discussed in the last lecture. We are now going to talk about how to use Temple's method to give you a tight lower bound. For this, we have to calculate sigma, that is expectation value of H squared minus H expectation value squared, the variance. The calculation is straightforward. I am not going to bore you with the details of the integrals evaluated, but it's a reasonably straightforward calculation, and in the end of the day, you will get sigma given by 1/4 alpha square minus 3/2 alpha plus 3 by alpha to the 4. I will ask you to verify this result in an assignment. And of course, if you know how to evaluate the Gaussian integrals, which we have discussed in the last lecture as well, it should be pretty easy to calculate this result. Now, the tricky part of using Temple's method, of course, is that we need E1 to be able to write down what the bound is. Now, we do know that E0 is less than curly E psi. So that if we can make this quantity as small as possible, then we will get a very tight bound on E0. It will lie between curly E psi and curly E psi minus a small quantity. Now, before we proceed any further, let me make a few comments. The first one of these happens to be that instead of using E1 in this calculation, we can actually use E2. And the reason is simple. Our family of wave functions, the normalized Gaussians, are all orthogonal to the first excited state phi1 for the system. I can be sure of that despite the fact that I do not know what the ket phi1 is explicitly, for the simple reason that because of the symmetry of this system, I know that ket phi1 has to correspond to an odd energy eigenfunction, and all of these psi alphas are even. So actually in our expansion of the ket psi, C1 is really 0 and we can forget about it, and instead of starting with the overlap between H minus E0 psi and H minus E1 psi, I could have very well have started with the overlap between H minus E0 psi and H minus E2 psi and developed a formula which was very much along the same lines with just E1 replaced by E2. So what we will do is we will use E2 here instead of E1. The reason behind that is obvious. E2 is bigger than E1, so E2 minus E curly E psi, the gap will be even bigger. That will make our bound up here even tighter. So what we are going to do is estimate sigma by E2 minus curly E psi. But the important point is we still do not know how to calculate E2. And we really don't know how to calculate E2. We could have estimated E2 using the variational method, but there is a better approach. The better approach is simply to figure out that E2 has to be more than a particular quantity. And so if we replace E2 by that lower bound of E2, then the denominator here, the actual denominator, E2 minus curly E psi, will actually be bigger than whatever estimate we are putting in, which means the actual bound will be even tighter than whatever we are calculating. So what we are going to do is find a value which definitely gives the lower bound to E2. And to do that, what we use is this very simple identity. You can show that x to the 4 by 2, the potential we have, is greater than or equal to this quantity omega square x square by 2 minus omega to the 4 by 8, as long as omega is real, hence omega square is positive, for all values of x. There is really no mystery here. All we are really doing is taking the inequality, the obvious inequality, half of x square minus omega square by 2 whole square is greater than or equal to 0, and just change sides a bit. Now the reason why we have done that is while we do not know how to find the energy eigenvalues and eigenfunctions for this particular potential, we do know how to find all the energy eigenvalues for this potential, which is nothing but the harmonic oscillator potential with just a shift, a constant shift in the energy. And because this potential is always bigger than this potential, the energy levels for this one will always be higher than the energy levels for this one. So what we get is, in general, the nth energy eigenvalue for x to the 4 by 2 will definitely exceed the energy eigenvalue for this one, which means it's going to be greater than or equal to n plus half omega minus omega to the 4 by 8. And this is going to work no matter which omega you use. Which means even if you use the omega which maximizes this expression, you would still get En bigger than that. And if you just do a very straightforward calculation with elementary calculus, you will realize that the highest value which this expression can take as omega varies over the entire real number line is given by this quantity, 3 by 8 to n plus 1 to the power 4/3. And this gives me a bound, a lower bound, on each and every one of the energy levels En. In particular, for n equals 2, it gives me this particular bound, 3 times 5 to the 4/3 by 8, which is around 3.2. Now let me point out that at this stage you might even wonder whether we have already gotten to our final result, because this also gives me a lower bound for E0, which is simply 3/8 or 0. In fact, this is exact, 0.375. So what we know from variational method is that the energy eigenvalue is less than 0.541 for the ground state. And we now know, because of this fact that x to the 4 by 2 is always bigger than this particular harmonic oscillator potential, its ground state energy has to be bigger than 3/8, which is 0.375. So we have managed to sandwich our ground state energy between 0.375 and 0.541. This is already an improvement over what we did using the variance. There the spread was a bit higher. We have improved upon things a bit. But actually what you will soon see is the Temple's method does a much better job of tightening the bound. So let us now take this value of E2. Of course, this is not the value of E2. E2 is always greater than or equal to 3.2. So let us take that and plug it into Temple's inequality, and we will end up with this bound for E0. E0 has to be less than or equal to this expression, which is of course what you have found from the standard direct application of the variational principle. And on the other side, what we have is, this is curly E psi, the expectation value in the state psi. This thing here is sigma. This of course is curly E psi again. What we should have here is E2, but what we have put in is a bound on E2. This number is smaller than whatever E2 is, which means that the denominator after I put this in is actually smaller than whatever E2 is. What that means is the bound which Temple's principle gave us, this is actually looser than that. This number is actually smaller than what Temple's actual bound is. So when we put in 3 into 5 to the 4th third by 8 in the place of E2, we are actually underestimating the left hand side. So whatever Temple's bound is, this is slightly looser bound than that. But since we do not know what E2 is, this is actually the best we can do. So the upshot of all this is, we know that E0 has to be smaller than this right hand side expression for all values of alpha, and it has to be bigger than this left hand side expression in orange, again for all values of alpha. And what this gives us is the freedom to choose alpha in such a way that firstly we would like to minimize this upper bound, make it as low as possible, but that is exactly what we do in the variational principle. On the other side, what we could do is choose a different value of alpha to make this expression as large as possible. Since E0 has to be bigger than this for all values of alpha and smaller than this for all values of alpha, choosing alpha differently for the two expressions is perfectly fine. It just helps us to tighten the bound on E0 a lot more. Of course, choosing alpha which minimizes this is something we have already done when we try to find out the estimate using the variational method. To choose alpha to maximize this takes a bit more effort, a numerical calculation rather than an analytical one. However, it's pretty straightforward to figure out the bounds, and when you do that, what you end up with is this. You end up with a bound for E0 which is between 0.541, this of course is the bound that we had found from the variational method, and 0.517 on the other side. So notice that we have been able to rather tightly constrain the value of E0, and as we have seen, our estimate for E0 from the variational principle is really not very bad at all. We had estimated it to be 0.541, and we know that it cannot be much below that because the lowest possible value it can have is 0.517. So this actually reinforces what we started our lecture with, that the variational bound that we get is actually much better at estimating the ground state value than we would often give it credit for. The next system for which we are going to use the variational method is the helium atom. This happens to be a very important application in the history of quantum mechanics. The helium atom happens to be a non-integrable system. At least the classical version is non-integrable. What that means is that it cannot be reduced to an action angle formalism, and as a result, it was impossible to use the standard Bohr-Sommerfeld quantization technique that old quantum theory used here. And any attempt at sort of getting an approximate result which improved upon the Bohr model results for the helium atom turned out to be very, very inaccurate. We are very far away from the experimental results that were already available. The determination of the ground state energy of the helium atom, or more precisely, an estimation of the ionization energy of the helium atom by the method that I'm going to outline right now, the variational method, happened to be one of the first major non-trivial successes in quantum mechanics. And it went a long way towards establishing the new theory as a really acceptable theory of the physical world. So let me now first describe what the problem is. The helium atom, of course, consists of one nucleus with charge 2, let's call it charge Z because we will generalize to helium-like atoms or ions soon, and 2 electrons around it. So basically, if you take the kinetic energy of the electrons and the potential energy of the interaction of the electrons with the nucleus, what you get are these 4 terms here, which together make up H1 plus H2, where H1 and H2 are just Hamiltonians which pertain to electron 1 and electron 2. In addition to this, what you have is this interaction term H12 between the 2 electrons, which is simply the Coulomb interaction term 1 by mod of R1 minus R2. As you must have realized from the form in which this Hamiltonian is written, we are using special units here. In fact, we are using what are called atomic units, where radius is being measured in the units of Rb, the Bohr radius, 4 pi epsilon 0 h cross square by me square. So in our theory, Rb is 1. And the energy is being measured in units of epsilon 0, where epsilon 0 is m e to the 4 by 4 pi epsilon 0 whole square by h cross square. And this is actually 2 Rydbergs in our conventional units, but in our atomic units, this is equal to 1. Of course, the adoption of atomic units helps us to write down the Hamiltonian without a lot of the messy factors of h cross m, e, and so on. Now, you must also realize that if I had just these first 4 terms, and the term in purple, the interaction between the electrons were missing from the Hamiltonian, then the Hamiltonian would have simply split up into 2 identical Hamiltonians, one for a single particle going round the nucleus. And so basically, in that case, the problem would have been easily solvable. If you know how to solve the hydrogen atom, you would be able to solve this particular problem with H equal to H1 plus H2. It is the extra H12 term which is going to make this problem really difficult to handle. While this extra term is going to cause a lot of difficulties, we can start our solution by ignoring this term to begin with. Of course, if I were to ignore this term, I would end up with exactly 2 copies of the hydrogen atom problem, and then I would know that the wave function, which is a function of both R1 and R2, can be written as a product of a function of R1 and a function of R2. This is, of course, without the 1 by mod of R1 minus R2 term. And there I would have also known that phi of R1 and phi of R2 would have been, at least for the ground state, simple decaying exponential functions of R, because they would just have been the hydrogen atom ground state wave functions. Now, what we are going to do in order to use our variational method is start with a family of trial wave functions, and the form of trial wave functions which we will use will capture the physical idea that we gave just now. If the perturbation term or this extra additional interaction term in the Hamiltonian could be ignored completely, then the wave function would really have been phi 0 r1 times phi 0 r2, where phi 0 is the wave function you have for the hydrogen atom. And that is z to the 3 by 2 by root pi e to the minus zr in the atomic units. Now what we are going to do is we are going to assume that our trial family of wave functions is of the form phi of r1 into phi of r2, and the only difference that I am going to make here is that instead of using the actual nuclear charge z, we are going to use a quantity called z1 in its place, and this z1 is going to be treated as our variational parameter. So we have a family of wave functions where as we vary z1, the wave functions change. Notice that by doing this, we are actually following our basic principle that our trial wave function should capture the basic properties of the physical system as closely as possible. Of course, this is a very simple-minded choice, and we would expect to be able to improve upon this by choosing better family of variational wave functions. But as we will soon see, even this simple choice actually gives you a rather good final result. There's also a reason why we would believe that the wave function looks somewhat like this. Notice that now that we have two electrons surrounding the nucleus, the job of each electron would be to essentially shield the other from the full effect of the nucleus by acting as a sort of negative charge screen around it. So it sort of stands to reason that what each electron will see is something like a nuclear charge which is slightly less than Z. So what we expect is that we will end up with a wave function which sort of looks like the hydrogenic wave function, but with a Z which is not the nuclear charge but slightly smaller. Z1, as we will soon see, turns out to be less than Z, and that sort of captures the fact that the other electron is screening the nucleus and hiding some of the positive charge of the nucleus from this electron. Now what we have to do, of course, is to find out the expectation value of the Hamiltonian using this trial set of wave functions, and the results we already know for the hydrogen atom come in very handy in calculating many of these final integrals that are involved here. I'm just going to quote the results for you at this stage. The details of the calculation will be left as an exercise. So for the hydrogen atom with Hamiltonian H1, single electron Hamiltonian, the expectation value works out to be Z1 square by 2 minus ZZ1. There is a very easy way of figuring out this result starting from the hydrogenic results. We are going to discuss how this is carried out in practice in the assignments. H2 has an identical result because, of course, H2 and H1 are identical Hamiltonians, and the sum of H1 plus H2 has an expectation value for this trial family of wave functions given by Z1 square minus 2ZZ1, just double of this value. Calculating H12 means that you have to integrate 1 by mod of R1 minus R2 times e to the minus Z1 R1 e to the minus Z2 R2 over all possible directions and all distances. And if you carry out the integral, which by the way is not too difficult to carry out, you just have to be a bit careful about the order in which you carry the integrals out, the result that you get is 5/8 Z1. Once again, the details of this calculation will be in an assignment. But when you combine all of these things together, what you get is that the expectation value of H for our trial family of wave functions turns out to be Z1 square minus twice Z1 into Z minus 5 by 16. And once we write the energy expectation value in this form, it is easy to see that its minimum value is achieved at Z1 equal to Z minus 5 by 16. This is simply a matter of completing the square, and that the minimum value which the expectation value of H takes, is Z minus 5 by 16 whole square with a minus sign in front of it. So our variational estimate for the ground state energy of the helium atom turns out to be minus Z minus 5 by 16 whole square. This, of course, is in atomic units. One atomic unit is 2 Rydbergs. So double this, you get the ground state energy of the helium atom in Rydberg units. And notice that what we are saying here is that the electron is screening the effect of the nucleus. It's not Z minus 1, which you would get if the second electron were to completely shield the nuclear charge by its own negative charge. But it does a partial job of it, which is why you are getting less than 1 here. But it sort of fits with the picture that one electron is screening the other one from feeling the net effect of the nucleus. So how does the result of this simple-minded variational calculation match up with experiments? After all, physics is an experimental subject, and the proof of the pudding, as they say, is very much in the eating here. Now, it is very difficult to experimentally determine the ground state energy of the helium atom or helium-like ions. It is much easier to find out the ionization energy, which is the amount of energy it takes to take one electron out of this 2-electron system and remove it from the atom or ion or whatever you have. And it is very easy to figure out what that is going to be. The ionization energy, which we are calling J, is the energy after one electron has been completely removed, which is just the energy of a single electron in a central nucleus, so just the Kepler energy term, minus Z square by 2 in atomic units. From that, you have to take away the energy which the electron already had, the 2-electron system had. So you have to subtract E0 from there. This, of course, is the actual ground state energy of the helium atom. So, using the variational method, what we get is finally, when you subtract minus Z minus 5 by 16 whole square from minus Z square by 2, this is the result that you actually end up with. This is a variational result for the ionization energy. Since the atomic unit is 2 Rydbergs, this expression expressed in the more familiar Rydberg units turns out to be Z square minus 54Z plus 25 by 128 Rydbergs. Now just to compare this with another standard method for estimating energies, the perturbative calculation, which we are going to do later, turns out to be Z square minus 5 by 4Z Rydbergs alone. So if you use the perturbative method for calculating the energies, which will be our next topic, by the way, you end up with the first 2 terms in the variational result, but the variational result tells you that there is an extra amount which is required for the ionization energy, which the perturbation theory ignores. Now, which of the two is going to be better as far as experimental results are concerned? To see this, what we are going to do is we are going to compare experimental values of ionization energy with these 2 quantities. Ionization energy calculated by the variational method and ionization energy calculated by the perturbation method for different helium-like systems. Remember, helium-like systems are systems which have one single nucleus and 2 electrons. So you could have H minus, the neutral helium atom, lithium plus, beryllium double plus, and so on. And the table below gives a comparison of these data. So notice that the experimental values are given up here. These are all in Rydberg units. And the perturbation theoretical values are given below. And the perturbation theoretical values are all smaller than the actual experimental values. In fact, the H minus result is rather bad because it even gets the sign wrong. Well, if you were to move to the variational method calculation, which actually gives a larger value than the perturbation theory calculation. Remember, there's an extra positive term in the end. it's easy to see that we are going to move closer to the experimental values. In fact, the variational results are given in this column, this row here, and they are a lot closer to the experimental values than what perturbation theory gives you. Well, you might, of course, still object that even the variational method gives you a negative value for the ionization energy for H minus. And what that means is, according to both the perturbation theoretical calculations and the variational method calculations, what you are getting is that the H minus ion will actually gain by losing the electron. That is, losing the electron would actually lower its energy. It will not take extra energy to lose the electron. But that is actually not correct as far as experiments are concerned. Experimentally, it takes some energy to make the H minus ion lose its extra electron. It takes a lot more energy to make helium lose its extra electron, and much more for lithium plus and beryllium double plus. That's easy to understand. Larger central charge means it's more difficult to get an electron away from it. Of course, none of these results are exact or are perfect. However, you would agree that the variational method does agree much better than the perturbation method does. And even the result for H minus, which is a bit of a problem, is not really that much of a disaster, simply because of the fact that we have used a very simple-minded variational calculation here. We have used a trial set of wave functions, which is very, very simple. We have just taken the hydrogen atom wave functions, put in a parameter z1 instead of z there, and multiplied them together to get my variational wave function. We can actually carry out the variational calculation to a much higher degree of sophistication. It turns out that we can explain the experimental values for the ionization energy to very high degree of accuracy by doing a slightly more involved calculation. By the way, let me also confess that in order to compare the variational and the perturbation method results, what we have used is a very simple variational method. We have also used the simplest result in perturbation theory, that is first order perturbation theory. You carried out perturbation theoretical calculations to higher orders, you would definitely improve upon the results that we have shown here. What I would like to impress upon you is this result comes pretty close to the experimental values, and given the fact that this system resisted all classical and semi-classical attempts at explaining these experimental quantities, I would say that variational method has done a pretty great job. And as I said, this was one of the first successes of full-fledged quantum mechanics. We will have more occasion to use the variational principle for estimation of energy levels of systems in future work. However, let me end this discussion on the variational method for the time being by showing you an application of the variational method not to determine energy levels, but to prove a very important theorem. This theorem happens to have an exact counterpart in classical mechanics, and maybe you have already know of the result in classical physics. It's called the virial theorem, and deals with a situation where the potential energy describing the system is a homogeneous function. That is, if you scale up the coordinate, here I've called it x, but it could also have been r. If you scale it up by k, some constant, then the potential is going to change by being multiplied by a power nu of k. So this nu is called the order of the homogeneous potential, and there are plenty of potentials for which this works. For example, the Kepler potential has nu of -1, right? 1 by r. The harmonic oscillator potential has a nu of 2. Now, for any wave function psi of x, the expectation value of the kinetic energy and the expectation value of the potential energy are simply given by these very familiar expressions, where n, of course, is a normalization constant. And just by going over from psi of x to psi k of x, where k is a label which I put on the wave function. So now I have a family of wave functions which is defined to be shy of kx. So by changing the value of k, I'm going to get different wave functions here. And what will happen if I did that is very easy to figure out. The normalization factor, for example, will simply pick up a 1 over k. Why? Because, well, let me just show you this one. Normalization factor, this integral will become integral of dx psi star kx psi kx. And if we were to substitute kx equals z, then this term will have to become dz by k. So if you take the 1 by k out, the rest of the integral is of course n. So you get a 1 by k times n. It's equally easy to figure out what happens to the kinetic energy and the potential energy expectation values as you change k. The kinetic energy will become an extra factor of k square, which essentially comes from the two derivatives that you are doing. And the potential energy will get an extra factor of k to the minus nu. Again, something which is pretty simple to figure out. So as a result of doing this, the expectation value of the Hamiltonian will depend on small k, and its dependence will be like this. So far, whatever we have said would work for an arbitrary family of wave functions. But let's just say that our family of wave functions happen to contain an energy eigenfunction in it. That is, psi of x was really an energy eigenfunction. Then our family would exactly contain an energy eigenfunction. And you will achieve that energy eigenfunction for k equal to 1. In other words, this expression for curly E of k has to reach a minimum when k is equal to 1. But that simply tells you that differentiating this expression with respect to k and then putting k equal to 1 will give you 0, because that's what you get for a minimum. Differentiating this with respect to k immediately gives you 2k expression of t minus nu by k to the power nu plus 1 expression of v. This has to be 0 when k is 1, and this immediately gives us this very important result, that twice the expectation value of kinetic energy for a situation where you have a homogeneous potential is actually nu times the expectation value of the potential energy. So just to look at the two special cases that we mentioned, the Kepler problem, nu is minus 1. So you get this very well-known and familiar result that in the hydrogenic system, the kinetic energy expectation value is minus half times the potential energy expectation value. And for the harmonic oscillator, nu is 2, and that gives you the result that kinetic energy and potential energy have the same expectation value for the harmonic oscillator. I'm pretty sure both of these results are very well known to you, and you have definitely used them in earlier applications. So this brings us to the end of our discussion of the variational method for the time being. As I said, you will see the variational method being used later in many other problems and many other versions. For the time being, let us wrap up this topic. We are going to talk about perturbation theory next. Until then, goodbye.